Recording. Now we are. Okay, hello. Trying this again. All right.
Take two.
There's this thing called proof by mathematical induction. You have all learned this from me in either Precocity or functions. And then we did it again extensively in logic. What is so-called mathematical induction? It is a process or method or theorem or axiom or something which says that for any possible property whatsoever, if you can establish that 0 has that property and that for any number, when a number has that property, then the next number has that property. If that's true, then all numbers have that property. Okay. Does everyone basically remember this? I mean, from Precocity or functions? Good.
Your brackets are weird.
My brackets are weird? No, they're perfect.
Missing a...
Nope.
Wait, no, I didn't.
I'm missing it.
Okay.
Right, because if it's true of 0, and if that's true, then that's true. Okay, so good. Now, in Precocity and functions, I alluded to the idea that this was an axiom of the natural numbers, and in logic, we definitely made it an axiom of the natural numbers. Note that Gossett does not do it that way. He takes the WAP as an axiom, and in fact, we can prove induction from the WAP, which is something that we're going to do next class. So for today, what we're going to do is just do some induction, man. And however, since we're all experts, I'm not going to start with some stupid crap like some of the cubes or whatever. Just going to go right for the hardest possible kinds of proof that we ever did in Precocity or functions. Which in functions, I actually tried to put the hardest possible problem I could think of on tests and stuff. Whereas in Precocity, I went pretty easy on you. We did hard problems for homework. We went over them in class, but then on the test, I gave them pretty much easy ones. Says me. Okay, so here comes a really hard theorem. And we are going to cram in this theorem into the last 7 minutes of class. Let's go. Okay, and there's a big pie in it, so just get ready for that. Yeah, that's right, you studied. So this theorem says big pi is like big sigma, but with multiplication instead of addition. Okay, Adisha, are you cool with this? Make me cool?
Yeah, sure.
Okay, good. So this says starting with 1 and ending with n, taking the product of numbers of the form 1 minus 1 over 2 to the k, that's greater than or equal to 1/4 plus 1 over 2 to the n plus 1. This is completely not obvious at all, and I have no idea how to ever prove this except by induction. So what did we do in how was the style that we adopted? Once upon a time, we nicknamed the left-hand side of this expression like a sub n, and we nicknamed the right-hand side of the expression b sub n. This is just provided for ease of reference, and what it is therefore that we really need to show is that a sub n is greater than or equal to b sub n for all n. Okay, how? Well, by induction. We want to show that it holds for the first number under discussion, which is 1, and then show that if it holds for a number, then it holds for the next number. Cool? Say cool.
Cool.
Okay, does it hold for, so there is a base case, and the base case is when n is 1. Well, what is a sub 1? Well, a sub 1 says take the product of a bunch of numbers starting with 1 and ending with 1. So that's just one number, right? So a sub 1 is just 1 minus 1 half. So that's just a half. Cool? Am I going too fast or just right? Okay, b sub 1 is, well, now just put 1 in for n on the right hand side. Well, that's just a fourth plus, you know what happens?
Plus 4. You're good.
Oh yeah, plus 4. Which is a half. So base case true. Okay. And now we make the inductive hypothesis. And the inductive hypothesis is that it is true for a certain number n. So we are going to say that A sub n is indeed greater than or equal to B sub n for some n. So we pick an arbitrary n. And then what we're going to prove is that the inequality holds for the next number. And since if it holds for the first number, and whenever it holds for a number, it holds for the next number, then it must hold for 2. And if whenever it holds for a number, it holds for the next number, it must hold for 3, and then so on. Okay, good? Say good. Okay. You may need to turn the camera slightly to make sure I'm still in frame. All right. What is it that we know? What is our inductive hypothesis? All right. Well, personally, this big pie kind of scares me, so I'm gonna get it and make it go away. Because what is A sub n after all? A sub n is just 1 minus a half times 1 minus a fourth times 1 minus an eighth, and I keep going all the way until I stop when I get to n. So this is 1 minus 1 over 2 to the n. Agree? And my inductive hypothesis is that this is greater than or equal to 1/4 plus 1 over 2 to the n plus 1. So this is what I know to be true, this is what I've assumed. And from this, I want to prove something. What is it that I want to prove? Well, I want to prove that it's true for the next number. In other words, I want to prove that 1 minus 1/2 times 1 minus 1/4 all the way up to 1 minus 1 over 2 to the n, plus one extra factor on the end, 1 minus 1 over 2 to the n plus 1, is greater than or equal to 1/4 plus 1 over 2 to the n plus 2. Now, there are many ways to do these proofs. Many of them, especially if you're very smart, somehow you suddenly have all kinds of ideas. But I like to do it in one straightforward, sort of dumbed down kind of way, in which I try to make the thing that I want to prove look like the thing that I know. So don't object, because it's not the most elegant way to do this. But I'm just going to rewrite this ever so slightly as 1 minus 1/2 times 1 minus 1/4 1 minus 1 over 2 to the n. And basically I'm going to just divide both sides of this inequality by this guy. Okay? I'm certainly allowed to do that. And if I do that, I'm going to get this relatively gross, I don't know, some people got mad at me last period, so I'm getting defensive. If I divide by this, can we get a common denominator in our heads and also middle school flippy flippy? It's like 2 to the n plus 1 over 2 to the n plus 1 minus 1. Okay, and so here's where we are right now. We have a thing that we know to be true, because we know it because it's our inductive hypothesis. We have a thing that we want to prove, or at least it's one baby step away from the thing that we're trying to prove. So it's basically the thing that we're trying to prove. And the way I like to think of this now is look at this and just decide, is there another thing that if we could prove would just bring it all together and make everything great and we'd be done? What did you say?
If 2 to the n plus 1 over 2 to the n plus 1 minus 1 is less than 1.
Careful, because that's a 2 and that's a 1.
Oh.
So it's a little bit harder. But what I know is all this crap up to 1 minus 1 over 2 to the n is bigger than this. And what I want to prove is all that crap is bigger than this. So when I taught this, I always said that there's a wish now. George?
You wish that the right-hand side of the inequality in red is greater than or equal to the right side of the inequality in blue.
Yeah. I wish that this were true. Why do I wish this? Because if I could somehow prove that, then together with the thing I know, I would know that thing is greater than thing, which is in turn greater than thing. Thus I have blue. Good? Remember this? Okay. So now we can just kind of focus on this wish. Okay, good, we got 4 minutes. Let's prove that this wish is true and thus complete the proof. Well, I am going to pull a little move of like do like a -1 +1 in here because that's just, I'm just going to do that. So what I get, what I wish were true is that 1/4 plus 1 over 2 to the n plus 1 was greater than or equal to 1/4 plus 1 over 2 to the n plus 2 times, I think it's just prettier if I write it as 1 plus 1 over 2 to the n plus 1 minus 1. Everyone with me? Okay, now multiply out the right hand side, because then some 1/4s are going to cancel. Cool? Okay, these die. And now, like I kind of want to get rid of at least some fractions, so I'm going to multiply through by 2 to the n plus 1. Okay, so I get 1 is greater than or equal to 2 to the n plus 1 over 4 times 2 to the n plus 1 minus 1, plus, that just becomes like 1/2, right? Plus, that also becomes like 1/2 times 1 over 2 to the n plus 1 minus 1. Okay, now I'm going to kill the 1/2, or I'm going to subtract 1/2 from both sides. So what I really get is 1/2 is greater than or equal to, move camera if necessary, Ishan. 1/2 is greater than or equal to, I can also, if I take a 2 out of the top and bottom here, I get 2 to the n over 2 times 2 to the n plus 1 minus 1, plus 1 over 2 times 2 to the n plus 1 minus 1. I think I've done that right. Shit. Also known as great. Okay, now what? Multiply through by 2, so I get 1 is greater than or equal to 2 to the n plus 1 over 2 to the n plus 1 minus 1. Did you guys follow that? Wait, did I do that right? Yeah. I just multiplied through by 2. Now what? Move that over here. So that's 2 to the n plus 1 minus 1 is greater than or equal to 2 to the n plus 1. Let's see. Subtract 1. No. Do the other way. Add 1 to both sides. So that's 2, and that's 2 to the n plus 1 minus 2 to the n. Okay, that's 2 to the n times 2 minus 1. So that's that 2 to the n is greater than or equal to 2. Is that true? Yeah, that's true. True when n is greater than 1. Greater than or equal to 1. Okay, and thus, by throwing in some double arrows and going all the way back, I have proved the wish. And by proving the wish, I transitive property it together with the no, I get the blue, and then I do one algebra one step up, and I have proven my statement that it works for n plus 1, and hence it's true by induction. Cool? Okay, good. Bye, internet.